ನೀವು ಕ್ಯೂ ಕೊಟ್ಕೊಳ್ಳಿ ಸ್ಟಾರ್ಟ್ ಮಾಡ್ತೀನಿ. Hello students, welcome back. We have been doing the course on analog and digital electronics. So moving on to session 2. So in this session we are going to discuss the continuation of the previous topic, which was MOSFET. The only thing being, this session we will do more of depletion MOSFET. Not only that, we'll also go on to a new topic, which is biasing these MOSFETs. Before we go to biasing, we'll see some topics. So before I can start, let us see what is it that we did, or what is the expectation of this session 2. Upon successful completion of this session, the students will be able to analyze the performance of depletion MOSFETs, differentiate between JFETs and MOSFETs. Just in case you're getting confused, in the previous session we have compared BJTs versus JFETs, now, or FETs in general. Now what we are going to compare? We're going to compare the two types of field effect transistors, which are the junction FETs and the metal oxide semiconductor FETs. Finally, we are going to start designing the biasing circuits for MOSFETs. The reason I say start, because it's a slightly more longer topic which we will cover partly in this session and the remaining one in the next session. So quickly summarizing what happened in the first session. In the first session, we started by telling about the construction and operation of JFETs. Not only that, we also saw the construction of enhancement MOSFETs, plus the output characteristic curves and the transfer characteristic curves for the two devices. Just to cross check, what does output characteristic curves mean? Yes? Okay, right. So output characteristics means the output voltage versus the output current, while transfer characteristics would mean the input voltage versus output current. So that's the difference between these two curves. We have done the enhancement MOSFET. Okay, with that recap now, let us quickly start the topic for the day. This is what we call as the depletion MOSFET. Now, looking at the construction here, can you directly identify what is the main difference now between the enhancement and the depletion? This we're going to see here by looking at this particular region here. If you closely observed, even this has the source terminal, the gate terminal and the drain terminal. It is also a 4-terminal device, so it also has a substrate. But what is the difference then? If you observe very carefully, now I have not applied any bias to any of the terminals here. They are all unbiased. When I do that, we already see a channel here between the source and the drain, which is of N-type. That's the difference between a depletion MOSFET and an enhancement MOSFET. That is, in a depletion MOSFET, even though there is no gate voltage applied, we already have a channel between the source and drain. This is very similar to what was there in JFET. If you remember, in JFET, there was already a channel between drain and source. We applied a negative voltage and we depleted that channel to the point where the device got cut off. Similarly here also, we already have a channel here. So is there a way now in which we can deplete this further? Answer is yes. Is there a way in which we can enhance it further? The answer to that also is yes. This is a very interesting device which we will now see in the next slide. So just quickly summing it up, it has a source there, it has a gate and a drain, and it's again separated by a oxide here, a thin layer of insulating oxide, which we call as a SiO2 or a gate oxide. Okay, so let's move on then to the next slide. This is now a P-type depletion MOSFET. Okay, so what is the only difference here now? The channel previously was of N-type, now the channel will be of P-type. Okay, the source and drain will be of P+. Okay, they are heavily doped, whereas the P channel that is formed is of moderately P-type. Rest all will remain the same. Okay, the difference is there you had a P substrate, now we are going to have a N type substrate. Now I have a question for you students. Now we keep saying P plus and P. So can you guess what's the difference between these two? When I say P plus, I say it is heavily doped, and when I say P, it is moderately doped. We also have in some cases what we call as P minus, which could be as a lightly doped semiconductor. The difference here is conventional pattern of doping is for every 10 raised to 8 silicon atoms you add one dopant. So that is the ratio, 1 is to 10 raised to 8, that we call it as a moderately doped. Heavily doped would be maybe 10 times more, 20 times more, or even 100 times more, and lightly doped would be much lesser than that. Now moving on, so let's do this. So this is an N-type depletion MOSFET and a P-type depletion MOSFET. Now what are the particular symbols for these devices? Again, depends on whether you want to use it like a 4-terminal device or as a 3-terminal device. Accordingly, you either have the description for 4 terminals or you have a description for 2 terminals. Okay, sorry for that. Okay, yeah. Okay, so let's quickly go back to the symbol here. So this is a symbol that we are talking of. Okay, so what's the difference then? The difference is we have 4 terminals here and we have 3 terminals here. Again, for N type we have the arrow mark going in, and for the P type we have the arrow mark going outside. Otherwise the representation is same as it was for a enhancement MOSFET. Now, is there any other difference? Can students spot that? Right? It all is the same, right? So just by looking at the symbol, how can I tell whether it's a depletion or it's an enhancement? Any answers for that? Yes, you are right, right? So the way in which you show the connection between the drain and the source. So the connection between the drain and the source, which I can pinpoint to you here. So what was happening there is, if you can see here, this particular line here, it is a solid line, whereas if it was an enhancement device, we used to have a dotted line, right? Means dotted line means what? There was no channel. The channel comes into existence only if we apply a appropriate gate to source voltage. Whereas in this case, even though you are not applying any gate to source voltage, there is already a channel between drain and source. So that's the only difference as far as a symbol is concerned. Okay, so now moving on, let us see if I were to plot the characteristics of this MOSFET. So what would I do for that? Okay, so typical connection would be, again I would start doing it by initially not applying anything at the VGS, but try and see what happens if I increase the drain to source voltage. So do you expect any current to be there? In case of an enhancement MOSFET, when VGS was 0, we said it was cut off. In this case, if VGS is 0, can any current flow from drain to source if you apply an appropriate VDS? If you say the answer is no, then you are confused, right? Even though VGS is 0, there is already a channel which exists between drain and source, right? So that's the reason we can have any current which flows from drain to source. I don't need to have a gate to source voltage at all. So even though I am shorting the gate to source, there will be a channel already existing. The moment I apply a positive drain to source voltage, now I start having the current which flows from the drain to the source. In other way, we say that the electrons get attracted towards the positive. So the flow of conventional current is opposite to the flow of electrons. So we say the current flows from drain to source. So even if there is no VGS, we are going to have the drain current. Now what will be the nature of this current with increasing VDS? Again the answer would be, larger the value of VDS, larger would be the current that flows. But does it go on increasing like that forever? No, right? Very similar to enhancement MOSFET, even here also we have a pinch off phenomenon entering. So beyond the pinch off voltage, even though if you increase the drain to source voltage, the current saturates and does not increase. So this is evident here if we look at the curves here. Okay, so this is a curve. This is the one which is showing the principle of operation, very similar to the enhancement MOSFET. This is the curve that I was talking about, right? So if you look at the behavior here, when VGS is 0, I am here, right? Even when VGS is 0, if I go on increasing the VDS, the current increases initially till I reach a point which is called as a pinch off point. In this entire region, I behave like an ohmic region, right? What does ohmic region mean? V is proportional to I, which is a straight line curve. That means it behaves like a resistance. This is one application which we'll use later that we'll see. Now, beyond pinch off, even though you increase your VDS, the current sort of saturates. This region we call as a saturation region. Now, how can you reduce the current further? You can reduce the current further by depleting this channel. So, how can you deplete the channel? The channel is already existing there. How can you deplete the channel? You can deplete the channel by giving a negative gate voltage. For this, let us go back to the previous slide and see what happens if I give a negative gate to source voltage. So this here, okay, I'll just go back here. You can see here, this particular region here, if I want to deplete the channel, what I should be doing? If I want to deplete the channel, then I should be able to reduce the gate to source voltage so that this particular region over here, it was already having a channel there. Channel means what? The channel is made up of N type. Now, if I connect a negative voltage here, what will then happen? This negative voltage at the gate will push these electrons deep into the substrate. Okay. Now, where are these electrons? All these electrons are there in this entire channel. So, by applying a negative gate voltage, what I am essentially doing is I am pushing them back into the substrate. So, essentially what that means, I am reducing the depth of the channel or I am depleting the channel. Okay, that's the reason we call this as a depletion mode device. You can actually deplete the channel by applying a negative gate voltage. Okay, so let's go back here then to the curve and see how this actually affects, right? So as you can see here, by applying a negative gate voltage which is -1, -2, -3, what I am essentially doing is I am now reducing my current. Earlier at VGS equal to 0, the current was 4 milliamperes. Now it is going down to 3, 2, 1 and so on. The shape of the curve is going to remain the same, in the sense I am going to have an ohmic region, I am going to have a saturation region, I am going to have a pinch off. But the onset of the pinch off, the onset of the saturation current will vary. If my saturation is happening at 4 milliamperes, then the pinch off was happening at around 4 volts. If the saturation is at around 2.5, then the pinch off is happening at a much lesser voltage. So larger the negative gate voltage, earlier would be the onset of pinch off. Now this becomes, this entire mode, we call it as a depletion mode. Now apart from this, can you also give a positive gate voltage to this device? The answer to this is yes, as is evident from this particular chart here. I am giving VGS as +1 volt and +2 volt. Now by doing that, what am I doing? What will happen if I increase the gate voltage? In the sense, if I give a positive voltage to the gate, I am going to increase the depth of the channel. So increasing the depth of the channel is again like enhancing your channel or enhancing your performance or enhancing the current carrying capacity of your device. So a depletion MOSFET can also be operated in its enhancement mode. So that's the beauty of this device. You can use it as a depletion device, you can also use it as a enhancement device, and this is how the curves would look like. So that's one interesting feature of a depletion MOSFET. Now moving on, let us see the transfer curves. The curves that we did previously were called as the output characteristic curves. What were output characteristic curves? We already said output voltage versus output current. But if I want to have the transfer curves, then I need to have output current versus input voltage. So in our case, the input voltage happens to be VGS and the output current continues to be ID. So VGS would be, as is already told, it can be either 0, it can be negative on this side, it can also be positive. At VGS equal to 0, I still have 4 milliampere of current because the depletion MOSFET channel exists even at VGS equal to 0. How to deplete the channel? We can deplete the channel by applying a negative voltage, and as you can see, the current reduces to a point when it eventually becomes cut off. That means there is no longer any channel there. Enhancement mode, go on increasing on the positive side, the current will continue to increase. So that's a transfer characteristic curves for you. It can be either it be directly plotted from this curve of output, you can do a transpose from here to here, or you can also use the Shockley equation, which is again the square law current equation. Now moving on, we have done the construction of depletion MOSFET, we have seen the operation of depletion MOSFET, we have seen how you can use it in depletion mode or enhancement mode. We have seen the output curves and we have seen the transfer curves. So what is going to be the next topic for this particular device? We have studied all the three devices now. We are not going to compare N MOSFET to P MOSFET, but we are going to do a comparison between JFETs and MOSFET. There are many more parameters, but here I would like to highlight the most important ones for these comparisons. So a JFET, as you can see, again at VGS equal to 0, there is a channel. I can reduce the channel by increasing the negative gate to source voltage. So JFET can only operate in depletion mode, whereas MOSFETs, especially depletion MOSFETs, you can use both in enhancement as well as depletion mode, while enhancement MOSFETs can only be used in enhancement mode. Then coming to the impedance, we said JFETs are much better than BJTs because they have a high input resistance, like of the order of 10 raised to 9 ohms. If you thought that was big enough, MOSFETs are going to give you an even larger impedance. So that's a double whammy, like 10 raised to 9, 10 raised to 13. It's not just 4, it is 10 to the power of 4. So 10,000 times increase in terms of input impedance. That's again a huge part why MOSFETs have become so popular. Extremely low noise condition when you apply the signal at the gate. There is hardly any gate current which flows in a MOSFET because you have a insulator between gate and the substrate. The next one, we have, coming to the drain resistance, we have a very high in case of a JFET, which is around order of 1 mega ohms, whereas in case of a MOSFET it is much lower. Now moving on to the gate current, right? So this is the most important part again when it comes to gate leakage. Now the next one is the leakage current. So as I already said, there is no current that goes into the gate of a MOSFET. No means not literally no. In case of MOSFETs, we do have extremely small current which is of the order of 10 picoamperes. Pico, you know how much pico is? Right, 10 raised to minus 12 amperes, very small current. Whereas in case of a JFET, you do have in the order of 10 nanoamperes. Whereas in BJTs, it's in the order of a few microamperes, because we all know BJT, we do have the base current which is the primary reason why we have amplification. So there it was a current control, so you do have a base current there, so that's a base leakage, you can say that. But in this case, absolutely great parameter to have, extremely high input impedance, absolutely no leakage current, it's not going to load the source which is actually driving this. But then coming to construction, again the most important aspect is the fabrication of a MOSFET. Now there is a certain parameter that we call as self-aligned device. Now MOSFETs can be fabricated. Now during fabrication, you need to have the gate device or the gate region exactly between the source and drain. There should not be any mismatch or overlap. Now self-aligned fabrication allows this to happen in case of a MOSFET, which is a great plus point, and it ensures reliability of the device, and it also allows you to do a lot of compaction, thereby increasing the density of the device. Means you can have more number of devices per square centimeter or per square millimeter, as the case may be in case of VLSI. So this is how we can broadly classify between JFETs and MOSFET. There are many more, but this should be the main benchmark how you can compare these two. Now moving on, the most important topic for these MOSFETs. Now before I actually start with these topics, the topics that I'm going to cover, the one put in red is for this session, the next one would be for the next one. How to bias depletion MOSFETs and how to bias the enhancement MOSFET. So we have different types of biasing methods. Before I actually start, let us ask a question by saying, what do we mean by biasing? For that we need to move on to the board just to see a few concepts before we actually start this. So any answers? What do you mean by biasing? So typically in general English knowledge, what do you mean by bias, right? Like he or she is more biased towards me than towards other person. No. We are not talking about that sort of a bias at all. Now the primary application for any active device is what we call as amplifiers, right? So let us say this is an amplifier. Okay, so what does an amplifier do? Amplifier is supposed to amplify, right? No, that would be a silly answer. So essentially amplifiers are used to amplify the small signal. Now what is a small signal? Typically the AC signal. So we have signals like, I am taking an example of a sinusoidal signal like this. Now this could be of frequency 1 kilohertz, 10 kilohertz, and typically it will have an amplitude in the region of 10 millivolts or so. Because in electronics we deal with voltages which are very small, right? I mean 1 volt is the voltage at which modern chips operate. So we are dealing with 10 millivolt signals or even microvolts when it comes to low noise amplifiers. Okay, so whenever I say I want to amplify, so essentially a signal which I give it like this, which is having an amplitude of 10 millivolt, it should come out amplified. Generally they are inverted, but let's not go there. An amplification would be something like this, right? It will not change the frequency. The frequency means reciprocal of your time period. So if the time period was 1 millisecond, this time period will not change. The input will also have 1 millisecond and the output is also going to have 1 millisecond. But what is going to happen is the peak here was 10 millivolt. If I am amplifying it by a factor of 2, means what? The gain of 2. The amplitude will go from 10 millivolt to 20 millivolt. Now this is what is called as amplification. Now generally whenever I want to amplify, now I will be giving signals of various voltages and various frequencies. So one signal could be of this type, another signal could have a different frequency altogether and a different amplitude altogether. Another one need not be sinusoidal, it could be triangular. Now for all these signals, this amplifier should amplify with the same factor which is multiplied by 2. It should not be dependent on what frequency I am giving. It should not be dependent on what's the relative amplitudes which I am giving, to an extent of course. So for this to happen, which is an ideal situation of what we call as linearity or linear amplifiers, means what? Amplify all the signals with the same amount of gain. For this to happen, we have to ensure that the amplifier operates in a very narrow region which we call as either a linear region if it is BJTs or saturation region if it is the MOSFETs, as the case may be. For that to happen, now we already seen the waveform, right? What's the waveform? If I were to see the transfer curve of a MOSFET or output characteristic of a MOSFET, this would be the curve. So typically, if it is a linear region, I would like to operate here. If it is a saturation region, I would like to operate here. That means what? The voltage that I am applying here, VDS, based on what voltage I am applying, I am either in saturation or I am in linear. So this is what we call as a DC voltage. Now the amount of DC voltage that we have to give to this circuit, which ensures that your device is in an appropriate region, is called biasing. Okay, what does biasing mean? I give an appropriate DC voltage. For example, let us say I want to operate in this region. Okay, so I give an appropriate DC voltage. Let us say this is around 4 volts. I give around 4 volts, and then my signal will vary only in a small band between this and this. So this is your small signal, plus or minus 10 millivolts, whereas the DC bias would be 4 volts. So how to ensure that for the entire variations of this input signal, your amplifier continues to remain in the appropriate region is called as biasing. Okay, so let us go back and see the different types of bias that we have. So as far as the depletion MOSFETs is concerned, we have 2 types of biases, methods or methodologies, which is called as self bias and voltage divider bias. Okay, so let's start with the first one here. So with that, we'll have to take an example of how exactly this biasing is done. So I will draw a circuit here which will essentially tell how the bias method is done. The most simplest of them is what is called as self bias. The self bias involves, this would be the device. If it is a depletion MOSFET, how is the symbol going to be? Something like this. It's an N type. I am going to show the arrow mark inside. Okay, and this is a gate. Okay, so this is a gate. So this gate I am now going to connect and give an appropriate gate to source voltage. Okay, so how is this now? So this is going to be your N type depletion MOSFET, right? Why depletion? Because the channel is already there. Why N type? Because the arrow mark is going in. Now can I identify the 3 terminals? This is definitely the gate. Okay, this was of course the substrate and the source which are shorted, so that I am ensuring that I am using it as a 3-terminal device instead of 4 terminals. I am not using my substrate contact. So this becomes my source and this becomes my drain. Okay, and finally you are going to have a resistance which is called as RD. Okay, you also have a supply voltage which we call as VDD. Why VDD? Because I am connecting it to the drain, otherwise it's one and the same. So if I do a biasing like this, so I connect the plus and this, so what is now happening? If I am connecting the plus to the gate, that means what? I am applying a VGS which is greater than 0. So if VGS that I am applying is greater than 0, what will be the mode in which I am operating this depletion MOSFET? Is it enhancement or depletion? Yes, right, it is enhancement, because I am now increasing the channel depth by giving a VGS which is greater than 0. So this will then become your the voltage between the drain, okay, and the source. We call it as VDS. Okay, this is the positive terminal and negative. In a sense, if I am going to measure a voltage, D is at a higher potential than source. Why? Because current is flowing from the drain to the source. So that current I am going to call it as ID. So drain current ID flows from drain through this resistance RD, then drain, then source, and back to the ground. Now for this to happen, I am controlling it by means of a gate to source voltage called as VGS. Now what does biasing mean? Biasing is essentially trying to figure out what should be the value of RD. Okay, that is a design methodology. Now you may ask me, sir, in this entire design, where is the input signal applied? You are just showing a voltage source, you are just showing a resistance, you are just showing a depletion MOSFET and the bias voltage. But where is the actual AC signal? Okay, that we are not showing here. In practice, the AC input that we are going to give will be given through a capacitor at the gate like this. Why through the capacitor? Suppose if there is any DC level present in the input signal, that DC level will be blocked by the capacitors. As we all know, capacitors block DC, right? Why do capacitors block DC? Any answers for that? For that, the answer is to the capacitive reactance. So what is the equation for capacitive reactance? We all have studied this in networks, right? So capacitive reactance is what? Xc is 1 upon omega c, which is nothing but 1 upon 2 pi f into c. Now for a DC, what is the value of f? Okay. For DC, the value of f is 0, right? So if the value of f is 0, then this reactance tends towards infinity. Means what? It will not allow any signal which has 0 frequency to enter through it. So we say it blocks the DC. So this is how the inputs are given. We call it as a capacitive input, okay, a capacitive coupled input stage. So we give the input signal here. Once we ensure it is appropriately biased, you can get the output at the drain, and this is where you typically take the output. Again, we would like to have a gate coupled or a capacitance coupled output. So right now, let us not go to all that. Let us only concentrate on trying to find out what should be the value of RD and what is going to be its operating point. Okay. So let us just rub these two and let us start with our actual design goal, which is to find out what is the value of the VDS and the ID. As you can see here, what are the unknown quantities? The unknown quantities are VDS. I don't know what the VDS is. I don't know what ID is, and I don't even know what RD is. Okay. So let us understand this entire concept by means of an example. So what is a particular example? In this figure, okay, it shows a biasing configuration using depletion MOSFET. Now it is given that the saturation drain current is 8 milliamperes. So what is saturation drain current? If you remember the equation for depletion MOSFET, what was the equation for depletion MOSFET? I wrote ID is equal to, okay, I wrote ID is equal to IDSS, right, into 1 minus VGS upon VP whole square. Now what was VP? VP was your pinch off voltage. So IDSS is what? The drain saturation current at VGS equal to 0. Now this IDSS is given in our case as 8 milliamperes. So IDSS is given as 8 milliamperes. This is a given data. Let us see how we can go and design our circuit. And the pinch off voltage is also given. What is VP now? VP is a pinch off voltage. So the pinch off voltage is negative, right? Because this is a depletion MOSFET. Now what we have to do is, we have to determine the gate to source voltage. What is the VGS required? We have to find out what is the VGS required. VGS is the voltage between gate and source. We have to find out what is the VDS, and we also have to find out what is ID. Remember, IDSS is given, but ID is not given. Okay. If everything is unknown, it becomes very difficult, right? So in this numerical that we are trying to solve, we have been given the value of RD, and this has been given as 0.4 kilo ohm, right? 0.4 K means it is 0.4 kilo ohm, and it is also given that VGS is 2 volts. So apart from IDSS and pinch off voltage, we have also been given the data of RD is 0.4 K and this applied voltage is 2. We have to figure out whether it is equals to VGS later on, but the applied voltage is 2. So let's go ahead and start the actual solving for this particular thing. So what is the first thing that we have now? We have the given data, which is 2 volt. Now how is this 2 volts applied? This 2 volt, as you can see, this plus here goes to gate and the minus here goes to source. So essentially this is nothing but your VGS. Okay, this is essentially nothing but your VGS. So VGS is given as 2 volts. Okay. So the immediate question would be, now is it in a depletion mode or enhancement mode? If VGS is larger than 0, then I am in enhancement mode. So directly I can use this particular equation here. Okay, so when the data is given, IDSS is known, VGS is known, VP is known. So cannot not find the drain current ID, right? It is just a simple case of substitution. So I will go ahead and substitute this in this equation. So I'll just move on to this side. So what is ID now? ID would now be IDSS. IDSS is 8 milliampere. Again, do not forget this milli. In many cases, students, they sort of miss out on these multipliers. Okay, so 8 milliamperes is 8 into 10 raised to how much? Yes, minus 3. Okay, IDSS is written into the bracket 1 minus, what is VGS in my case? In my case, VGS is now 2 volts. So 1 minus 2 divided by, what is VP? Again, another possible mistake, right? VP is negative. So make sure you write minus 2 and this entire thing will go as square. Now what does this become? This becomes minus minus plus, 2 upon 2 is 1. So 1 plus 1 is 2. 2 square would be 4. So basically it is what? 32 milliamperes. So your ID will eventually come to be 32 milliampere. So I have now successfully found out one part of the operating point. Means what? I have successfully found what is the value of ID. If we then find what is the value of VDS, then the operating point is nothing but your value of VDS and value of ID. So let's move on now. How can you find out the operating point? For that, we need to have a basic understanding of what we call as Kirchhoff's voltage law. So what is Kirchhoff's voltage law then? Kirchhoff's voltage law is nothing that you can take any loop in an electrical network which consists of voltage sources, resistors. All you have to do is find the algebraic sum of these voltage drops and the voltage sources and you just summate it to 0. So in this case, let us try to apply that to a loop, output loop. So what is the output loop? Now what we are using on this board is what we call as single-ended notation. What does single-ended notation mean? I am showing here only plus VDD. What does plus VDD mean? I am actually having a voltage source here, the plus of which goes here, the minus of which comes to this. So if I were to rewrite this, how I would write? I would write a line here, a cell here, a battery here showing the plus and the minus of it going to this. Okay. So this is your actual VDD. So henceforth we will not use this. It's only the first time that I am trying to show how a single-ended notation works. Next time whenever I say plus VDD, you should know that this is how it is connected. So can you now apply the Kirchhoff's voltage law for this entire loop? So what do you have in this loop? I have a voltage source here. I have a current ID. So a drop ID into RD. Then I have a drop VDS. So sum up all this and equate them to 0. So the equation for KVL would be VDD minus the drop ID into RD, right, minus VDS would be equal to 0. Okay, just doing algebraic sum. You can go back to your basics of which one to take as plus, which one to take as minus. Okay, I am straight away using the conventions for KVL. We can refer some standard material for this reference. But I am only showing you which loop to apply and I am keep calling it as an output loop. Next time I am going to simply say applying KVL to the output circuit or output loop. So VDD minus IDRD minus VDS equal to 0. So what was my goal? My goal was to find what is VDS. Do I know VDD? Yes. Do I know ID? Yes, just now calculated. Do I know RD? Yes. So what is left then? Substitute these values and find out the value of VDS. So you can just go ahead and do that. We are going to get your final VDS as 5.2 volts. Okay. So what does that mean then? I started with a problem here which required me to do the biasing techniques. This is called a simple self-bias circuit which consists of one resistor and a direct DC voltage at the gate terminal. So my Q point is finally the value of ID and VDS. So how do I write the answer as? We write the answer as the Q point, which is nothing but your operating point or the bias point for this circuit with this value of resistor is nothing but we write it as VDSQ, which is the value of VDS at quiescent point, comma IDQ, which is nothing but the value of drain current at Q point, which happens to be in our case as 5.2 volts, comma 32 milliampere. So this essentially is how to find the operating point for this circuit. So if I were to draw this on a plot of VDS versus ID, what would I do? Okay, so essentially I'm going to show this here on this side. Okay, so this is going to be the plot. I am going to have VDS and I am going to have ID. Okay, this is what we call as the output curve, right? VDS versus ID is the output curve. Positive VDS, positive ID. So this is 0. So your 5.2 would be somewhere here. Okay, and your 32 milliamperes would be somewhere here, if you do it in terms of milliampere. So if you check these two, so this is going to be your operating point. Okay, so whether it is in the saturation region, yes, because we have applied the curve in the saturation region. So this is how the curve is going to be, right? So that means what? I am ensuring that by biasing it in this value, if you remember initially we said we have to give a certain DC bias so that I am in a particular operating point. So by using this technique of VDD and RD, I have ensured that I am going to be in the saturation region and I have enough leverage on either side of the saturation of the Q point, which enables me to have the uniform amplification for my signal. So that's the answer. The Q point is 5.2 volts and 32 milliamperes. Now, is this the only way in which we can do the biasing? Okay, or are there better ways of doing the biasing? Now, is this method of doing biasing good enough? The answer is no. Why? Because this Q point is supposed to remain stable irrespective of changes in the temperature. We all know semiconductor devices are extremely temperature dependent. Why? Because any increase in the temperature would increase the number of charge carriers by creating more electron hole pairs. So it alters the overall dynamics of any device the moment you have the temperature increasing. The opposite is the case when temperature decreases. So I need to have this Q point stable no matter what the increase in temperature is, or no matter what is the change in the process. By process I mean I will go and manufacture 1 billion such MOSFETs. Do all those 1 billion MOSFETs have the same gain factor? Do they have the same transconductance factor? The answer would be no. So despite the variations in process parameters, despite the variation in temperature, I would like to have a device or a circuit which has a very stable Q point. For that, self bias, even though it may seem very simple, is not the answer. So the answer to that is the most widely used one, which we call as the voltage divider bias. To understand the voltage divider bias, again we will take the help of a numerical example, wherein let us do the actual design technique. What does the design technique mean? I will give you the value of this thing, and you have to find out what is the value of RD, RS and so on. So let me just draw the circuit for you. Okay. So again this is also going to be based on a depletion MOSFET, since we are doing the biasing for depletion MOSFETs. So it is going to have a device like this. Okay, this is a source contact, and the substrate contact. Instead of one resistor, now we will have two resistors, one at the source, one at the drain, and the gate, instead of directly giving the voltage, we take the voltage from the power supply. So this is going to be the way in which we connect, and we eventually going to ground this, and this is where you are going to connect your VDD. Okay. So I am going to call this as VDD. This is going to be a ground. This is going to be a depletion MOSFET. Arrow mark going in, it is N type. So this would be your RD, or the drain resistance. This would be the source resistance. Why? Because this is drain, this is source, and this is gate. Okay. So whenever I am showing a solder dot here, that means there is a connection. And these two we call as R1 and R2. Now let me just run through the entire question here as to how we should do the design. So the question says we have to design a voltage divider bias network. Design means find RD, find RS, find R1, find R2. Architecture is known to us. With a supply voltage of VDD equal to 16 volts. So VDD is given, it is given as 16 volts. Then they have given what we call as the drain saturation current, okay, at VGS equal to 0, which is given by IDSS. I'll write this here. IDSS is given to us, and the value of this IDSS is 10 milliamperes. Okay. So two data given. Next, they are given the pinch off voltage also. And the pinch off, again it has to be a negative voltage. VP is given as minus 5 volt. Right? They have given the Q point already, we have to find R. So to have a quiescent drain current of 5 milliamperes, that means what? The drain current value is already given. Okay? The drain current value is already given, which you call as a disk Q point or a quiescent point. Okay? And that is given as 5 milliampere. Drain current is given as 5 milliampere, and the gate voltage is 4 volts. They simply say gate voltage is 4. Now where is gate? Gate is here. But we always keep saying gate to source. They are not saying gate to source voltage. They are only saying gate voltage. So gate voltage means what? The voltage at the terminal gate and ground, which we call as only VG. Just like VDD means voltage between this point and ground, VG means voltage between the gate terminal and ground. That has been given as 4 volts. Remember, VG is not equal to VGS. Okay, so this is which is given. Next is they have given that the drain resistance can be assumed to be of 4 times the value of source resistance. Okay, that is RD is given as 4 times value of source resistance. So this is the design goal which we have to do. Now let's straight away start applying the drain current equation. So what is the drain current equation? The drain current equation is ID is equal to IDSS 1 minus VGS upon VP whole square. Okay. What all we know here? We know ID given, we know IDSS given, VGS unknown, we know VG not VGS, VP is known. So putting everything here, the only unknown is VGS. So we can solve for VGS and we get VGS as minus 1.5 volts. Okay, you just have to substitute everything. What is left is VGS, which is minus 1.5 volts. Now, what does VGS mean? VGS is nothing but your nodal analysis says VG minus VS. S means VS means what? At this point. Okay, so VG minus VS is known as minus 1.5 volt already given. Now, what is the other unknown we don't know here? We already know VG, we know what is this VGS, find out VS. So therefore, we can find VS and this happens to be 5.5 volt. Remember, my overall goal is to find out what is this value of RD, what is this value of RS and so on. Now what is VS given by? VS is nothing but your voltage drop across the resistance RS. Now is the current across source same as drain? Yes, because there is no gate current. So whatever is ID here will be the same at source. So I will continue to have the same current flowing here. So VS I can simply write it as ID into RS. So this is nothing but your ID into RS. Now you already know VS, you already know ID, find RS. So RS will come out to be 1.1 K. Once RS is known, I am done with this. What is the next? Use this design assumption given to us. You have to take RD as 4 times RS. So RD is also known. So we can write RD as 4 times RS, which happens to be 4.4 K. So I found out RD, I found out RS. The last thing that is left is to find out R1 and R2. Now this is again a very simple step. go back to your network basics as to how to do a parallel divider formula. Vg is the voltage across R2. What is the overall voltage? 16. What's the voltage here? 4. So can I write the equation for Vg in terms of these two? Answer is yes. So Vg is given by, the voltage across R2 divided by sum of the two series resistors R1 plus R2 multiplied by the overall voltage, which is VDD. Here to here it is VDD, here to here it is Vg. So Vg is nothing but this voltage, this resistance divided by these two and this one. Okay? So applying this, we can straight away go and find out the actual value of R2, because actual value of R1 and R2. We have Vg known, Vd known, two unknowns. So we will make one more design assumption here. We will take R2 as 1K. So let R2 be 1K. So if you apply R2 as 1K over here, we are going to get R1 as 3K. Everything else is known here. You are going to get R1 as 3K. So with this, we have found out RD, we have found out RS, we have assumed R2 to be 1K, and using a voltage divider equation, we have found out R1 to be 3K. So with that, we would have completed the entire design equation for voltage divider bias. It may sound a bit lengthy, but once you start with the flow, it's a straightforward thing. So with that, we sum up this entire session 2. Let's quickly look back as to what was the takeaway from this particular session. So in this session, we started with the construction and operation of depletion MOSFETs. We saw the both output as well as transfer curves for depletion MOSFET. Then we saw what's the difference between a JFET and a MOSFET. Finally, we studied two techniques for biasing depletion MOSFET, which is the self bias and voltage divider bias. In the next session, we will be doing the same biasing techniques but for enhancement MOSFETs. Thank you.